Welcome to the lecture series of switching theory and logic design. Unit 4, we have discussed about sequential circuits part 1 and sequential circuits part 2. In this part 1 and part 2, we have completed the basics of sequential circuit elements like flip-flops, latches, almost all the basic elements we have seen for the digital technology. After that, we have seen different types of registers and counters. In the series of these lectures, now we will see one of the counter application. So that is RGB counter. RGB counter. This RGB counter now we will implement with the help of LogiSim and we will see the simulation results. Let us see first what is meant by an RGB counter. In the today morning, I got a mail from a student. The student is asking what is the solution for the problem. Here the problem is develop a counter circuit to lit RGB LEDs that is red, green, blue in the order as follows. This is a problem and the order is the first condition all the LEDs are of the off state and then it is going to the next state, all the LEDs are going to on state, next only red is going to on and next then it is going to green on, next it is going to blue color LED is going to on, next red and green are going to on and next green and blue LEDs are going to on and next last condition after completion of the 8th step is again it is coming back to the first step, that is all LEDs are going to half state. Here this is the given problem. Let us see the solution for the problem. So coming to the solution, to develop an RGB counter. So to develop an RGB counter, it requires a clock signal and it consists of 3 output LEDs named as red, green, blue. These are the 3 LEDs. Next coming to that, design of synchronous counter procedure is used to solve this problem. For solving this problem, I am taking the design procedure of synchronous counter. So whatever the design of synchronous counter procedure we have seen in the previous videos, the same procedure here I am using. Okay, next coming to that, the first step, draw the state diagram by considering the conditions, whatever the conditions I have taken in the problem, those conditions I have to take here. Next, the RGB outputs are representing with 3 bits. So coming to here, the synchronous counter designing procedure helps to implement any type of counter based on your request. Coming to the asynchronous counter, it has limited to some up and counting operations based on the different types of mod counting operation. It may be start from 0 and maybe it may be ended with 10, it may be ended with 60, it may be ended with 100, it may be ended with 1000. That is, it has a ascending counting operation, it may be descending counting operation, and it has some limited mod counting operations. So the asynchronous counter is not used for all the application. So here we are using the synchronous counter for developing any type of application by following the standard procedure. In that first step, we have to draw the state diagram. So before going to the first step, first understood what is the RGB counter. Okay, so see here the exact problem here I am writing. The first here the given conditions in the problem. First one, all the LEDs are in the half state. So I have switched off I am representing the states here with using some LED circuits. These are the LEDs, RGB LEDs. So first state, off state. So the half state I have represented here. Next, coming to that, 3 LEDs are going to on state, red, green, blue. 3 LEDs are switched on in this condition. Next one, only R is going to on, that is red color LED is going to on. Next condition, only green is going to on, only green is going to on and remaining 2 are in the half state. Next, only blue is going to on, so that is blue color is going to on, remaining 2 are going to off. Next, red and green, so red and green is going to on and blue is going to off. Next, green and blue is going to on and red is going to off. Next, last condition, turn it into first state. So that is what is the first state? All the LEDs are going to off. The same state I am represented here. So this is the given problem. Okay. So for implementing this problem, see here, the output we are connecting LEDs, but the LEDs, see here, the LEDs are we are programming the otherwise we are making a circuit arrangement to switch on the circuit and to switch off the circuit. That means if whatever it may be the color, we don't require that color for some time. So remove that color, and these LEDs are going to on and off. So if the LED is going to off, we are representing with 0. The LED is going to on, we are representing with 1. Okay. So color we will take at the last. Presently, forget about the color. Take just on and off conditions. Based on and off condition, write down here the binary values. If the LED is going to off, you have to represent 0. If the LED is going to on, you have to represent with 1. So see here, the first condition. All the LEDs are off. So in the first condition, I am representing with all zeros. Next condition, all the LEDs are going to on. So I am representing with 1, 1, 1. So these are the conditions I have taken for each combination. Red is only on. That is 1, and remaining 2 LEDs are off. 1, 0, 0. And fourth LED. So the middle LED is going to on, and the first and last LEDs are going to off. That is 0, 1, 0. Next, blue color LED is going to on. That means last LED is going to on. The first two LEDs are off. That is 0, 0, 1. And next condition, first two LEDs are going to on, last LED is going to off. That is 1, 1, 0. That is 1, 1, 0. Next, last two LEDs are going to on. That is 0, 1, 1. That is 0, 1, 1. Next, last three LEDs are off, and coming to that, I am representing with 3 zeros. If the LEDs are going to on, then you have to represent 1. Otherwise, if they are going to 0, if they are going to off state, then you have to represent with zeros. Okay, right. Now we have seen. So the states. If the first state is all the LEDs are off, you have to represent with 0. Next state is 1, 1, 1. Okay, after following that all the LEDs, that is we are representing with 1, 1, 1. If it is the present state, next state is 1, 0, 0. Based on this, now you have to draw the logic diagram. So these are the conditions, and next we have to draw the state diagram. So see here, this is the state diagram. So first condition all zeros, next condition 1, 1, 1, and next condition 1, 0, 0, and next condition is 0, 1, 0, and next condition is 0, 0, 1, and next condition is 1, 1, 0, and next condition is 0, 1, 1, and next condition is again you have to hit triple zeros. Next again you have to hit triple zero. This is a very important condition, and actually I have represented the 2 zeros. There is no next of here. You can remove 1 0. Okay. Okay, right. Now we have removed that 0, 0, extra 0, 0 combination. Now coming to that, these are the finalized states after drawing the state diagram. So totally here we have 7 different, 1, 2, 3, 4, 5, 6, 7. 7 different states. We have total 7 different states. It is starting from 0, 0, 0, and it is ending with 0, 1, 1 by considering of different types of state values here. Now let us write. So this is representing 0, and this is representing 7, and this is representing 4, and this is representing 2, and this is representing 1, and this is representing 6, and it is representing with 3. So the counter we are designing here. First, the condition here, the counting sequences are 0, 7, 4, 2, 1, 6, 3, again 0. So these are the counts we have to perform here. That means that whatever the concept we are taking, that counter is going to perform these counting operations. So first one is 0, next 7, next 4, next 2, and next 1, and next 6, next 3, and next 0. So these are the counting counts we are going to perform here. Okay, so this is the state diagram, and you have to analyze the states what you are doing here. Okay, so after completion of drawing the state diagram, then you have to move to the next step, that is writing the state table. With the help of state table, we are writing here excitation table. That is, first you have to write down the present state outputs, and you have to write down the next state outputs, and based on the present and the next state outputs, you have to identify the inputs of the flip-flops. Right? Here, which type of flip-flop you are going to use for constructing this counter, that is you have to decide. So for implementing generally the counters, we are taking the T flip-flop. Otherwise, you can take D flip-flop also. Presently, I am taking T flip-flops. Okay, by using T flip-flop, I am implementing this counter. So let us see the next step. So in the next step, first the basic one is the state diagram. By using this state diagram, now you have to form the state table, otherwise excitation table. If the present state is 0, 0, 0, what is the next state? That is 1, 1, 1. Okay, if the 1, 1, 1 is the present state, then what is the next state? That is 1, 0, 0. If the present state is 1, 0, 0, what is the next state? 0, 1, 0. Okay, so here I have 3 digits 0, 0, 0. Right? For representing this 0, 0, 0, I have to take 3 outputs. That is, I am representing each bit as Q2, Q1, Q0. Q2, Q1, Q0. So the present state output is Q2, Q1, Q0, and next state output is also Q2, Q1, Q0. Okay, so both are same. Okay, but that is the present state and this is the next state. That means now I am going to draw the excitation table. The present state is consisting of Q2, Q1, Q0, and next state is also consisting of Q2, Q1, Q0, and last I have to draw the inputs based on the selection of my counter. So I am selected T flip-flops for implementing my counter. So at the last I have to draw the T inputs. I have to predict the T inputs. Let us see the excitation table. So this is excitation table, the second step. So first step state diagram, second step is excitation table. In the excitation table, present state Q2, Q1, Q0 outputs, next state Q2, Q1, Q0 outputs. If the present state is 0, 0, 0, here I have used 0, 0, 0. This is my first state. So if 0, 0 is the present state, next state is 1, 1, 1 based on our requirement. So see here, all zeros, next state is 1, 1, 1. So the same thing I have written here. So this is the present state and this is the next state. So next coming to that, if you are taking the 1, 1, 1 is the present state, if you are considering this is the present state, then next state is 1, 0, 0. The next state is 1, 0, 0. That is I am writing here. So see here, if the present state is 1, 1, 1, next state is 1, 0, 0, 1, 0, 0. Like that we have to write the present state and next states. So for all the 7 states, you have to write down. Consider this is the present state, then what is the next state? Then write down this is the present state, then write down the next state. Next, write down this is the present state, then what is the next state? For all the states, you have to write down the present states and next states. So see here, 0. The first time writing, here it is 0. Next second one 7. Next one 4. Next one 2. Next one 1. Next one 6. Next one 3. So 0, 7, 4. 2, 1, 6, 3. Okay, so these are the states are available. These are the states are available. So see here, by using 3 bits, we can write the maximum 8 possible combinations. 0, 1, 2, 3, 4, 5, 6, 7. Okay, so but here we have written only 7. We have not written the 5th combination. That is, the 5th minterm is not available in this. So for that reason, you can take this 5th count as a don't care combination. This one you can take as don't care condition. You can take this one as don't care condition. That is very, very important. So I am taking 5th one as the don't care condition and remaining all the states are available here. For 0, what is the next state? 7. For 7, what is the next state? 4. For 4, what is the next state? That is 2. For the 2, what is the next state? 1. For the 1, what is the next state? That is 6. For the 6, what is the next state? 3. For the 3 present state, then what is the next state? That is 0. That is we are coming back to here. If the present state is 0, next state is 7. Like that we are doing the counting operation. Now you have to predict what are the inputs T2, T1, T0 you have to identify. So the excitation table we are defining like this. The excitation table is consisting of the present state outputs and next state outputs. Now you have to predict the inputs. Okay. So see here the next one. So I have taken here I have represented with some purple color the Q2 output of the present state, the Q2 output of the next state, and T2 of the input of the our flip-flop. So if this is the present state and if it is the next state, then what is the input? You have to write down here. Here the present state is 0, next state is 1. For T flip, see here, I have to identify, I have to think that I am using T flip-flop. For the T flip-flop, the output is 0. The next state output is 1. So the output is shifting from 0 to 1. Then what is the input? So we know the T flip-flop operation. If the T input is equal to 0, then there is no change in the output. If the T input is equal to 1, then the output is shifting from 0 to 1 or 1 to 0. That is, previous output is complemented to the next state outputs with respect to the clock. So T may be 0, T may be 1, but you have to give the clock signal. Okay, if T is equal to 0, then output is there is no change at the output. If T is equal to 1, then there is a change in the output. That is, previous output is complemented to the next state output. So see here, the previous output changed to the next state. So the input may be 1. The input is 1. Here you have to write like this. Here, the previous output is 1 and present output is also 1, then there is no change at the output, then the input of the T flip-flop is 0, right? Next, 1, 0, right? 1, present output is 1, next state output is 0. So there is a change in the output. So the input of T flip-flop is equal to 1. Next, present output 0, next state output 0, and the T2 input is equal to 0. Why? Because there is no change. Then present state is 0, next state is 1. Here we have a change, so for that reason the input is equal to 1. Here output is 1, next state output is 0, there is a change, now the input is equal to 1. And present output is 0, next state output is 0, there is no change, now the input is equal to 0. Now finally we have written 1, 0, 1, 0, 1, 1, 0. So these are the inputs we have predicted from the present state to the next state outputs. Now write down T2 expression here. So T2 is equal to sigma small m of. So what is the input combination here? Present state, the previous outputs. So here the previous state outputs are 0, 0, 0. That is, you have to write down T2 is equal to sigma small m of. Write down the input possible combination. Here the first one is 0. Write down here 0. Why? Because T2 is equal to 1. If T2 is equal to 0, don't take that input combination. If T is equal to 1, then only you take the input combination. Here T is equal to 1. You have to write down this combination. Next, it is 0. Don't take this combination. Next, you have to take this one, and take this. Don't take this one. So the first combination you have to take, and the third and fifth, sixth combinations you have to take. So here it is 0 and it is 7, 0, comma, 7, comma. So 7 we are not taking here. 7 we are not taking here. Why? Because it is 0. Okay. Next, this one 4, 0, comma, 4, comma. Next, this is 1, comma. Next 6. 0, 4, 1, 6. So this is the T2 Boolean expression. So see here, T2 is equal to sigma small m of 0, 1, 4, 6. Like in this way, you have to identify the T1. So see here, next T1, Q1 is the present state, Q1 is the next state, and T1 you have to predict, then you have to write down the T1 expression. So T2 we already know 0, 1, 4, 6, and T1 is equal to sigma small m of 0, 1, 2, 3, 4, 7. Okay, and remember 5 is the don't care condition. Next, Q0 present state, Q0 next state outputs, and T0 input. You have to predict the input in this way and write down T3, T2, T1, T0 combinations. So we got total 3 Boolean functions from the excitation table. From this excitation table, you have to identify T2, T1, T0 outputs. Next step, you have to minimize these functionalities. So third step, so take T2, T1, T0 expressions. For these 3 expressions, form the K-map and simplify these equations. So after simplifying the equation, T2 is equal to Q1 bar plus Q2 Q0 bar, T1 is equal to Q2 bar plus Q1 bar plus Q0, and T0 is equal to Q2 bar plus Q1. Now you have to draw the for 3-bit counter. Why? Because we have used 3 flip-flops. Why? Because we have 3 outputs. So RGB. So for 3 outputs, we are taking 3 flip-flops, and 3 flip-flops are the 3 T flip-flops, toggle flip-flops. Here we are taking. Okay, let us see. So this is our next step. So for implementing the synchronous counter, first draw the 3 flip-flops. So the synchronous counter means all the flip-flop has the the common clock signal input. So this is the clock signal. So this is the clock signal input, and the same clock is connected to the R flip-flops at a time. Okay. Now coming to the remaining circuitry. What is the input here we have to give? The input for T0 is equal to, we have written the expression Q2 bar plus Q1. That is, you have to take the Q2 bar output. So this Q2 bar output you have to take from here, and you have to connect an OR gate here. So for that OR gate, Q2 bar is the one input and Q1 is the another input. So like that we have to frame the connections. So this is the connectivity. So T0 is equal to Q2 bar plus Q1, and T1 is equal to Q2 bar plus Q1 bar plus Q0, and T2 is equal to Q1 bar plus Q2 into Q0 bar. So this is the expression. So these are the finalized simplified expression, and this is the simplified circuitry. Okay, right. So this is the implementation of RGB counter. This is the implementation of RGB counter. Okay, right. Let us take the simulation part. Let us take the simulation. Let us see the RGB counter implementation by using LogiSim software. Okay, so here, now I am opening the LogiSim software. So the LogiSim software is in a 6 MB file, and it is very less sized software, and we can use for the digital application purpose. Right. So this is the interface of LogiSim. In this LogiSim, here we have the toolbox here, wiring, gates, plexus, arithmetic, memory, and input and bias circuit. And next, coming to here, from memory you have to take the content. I already designed this circuit. Now I am opening the circuit. So this is the RGB counter. So see here, this one is the our T flip flop. So this is the first element, second element, third element. Total 3 flip flops here we are taking. So totally I am taking here 3 flip flops. First T flip flop, second T flip flop, and third flip flop. The output here it is T0, and this is T1, and this is T2. That means here I said that RGB counter we are implementing. The first color is R, next G green, next B blue color. So the red color you have to connect at the output of this T2 terminal. So previously we have written T2, T1, T0. Okay, so this is the T2 output. So this one you have to connect it to the red color LED. So this is the red one, and this is the green one, and this is the blue one, and this is the red, green, blue. These are the 3 LEDs here we have. Right. Now I am going to simulate this circuit. So see here. So now I have enabled this circuit. So see here, all the counts it is going to perform. Here the clock signal is going to activate these flip-flops in the different periods based on our connection procedures. So see here, all the flip-flops are going to off under on situation, only red color LED, and only green color LED, and only blue color LED, and red and green color LEDs are going here, and green and blue color LEDs are going to switch on here. So these are the conditions. Okay, so totally we have to get 7 different types of condition. In the first condition, we have to switch off all the LEDs. Let us see that combination here. Right, coming to here, we have total 8 conditions. So here totally we have 8 conditions. These 8 conditions we are going to see here. Right. So see these 3 LEDs. Okay. Let us see from here. Right. All LEDs are off. 3 red LEDs are going to on. First one, second one, third one, next. First 2, next. Second 2, next. All LEDs are going off. Right. So this is about the implementation of LogiSim software based RGB counter. So this is the implementation of RGB counter implementation by using LogiSim software. Okay, thank you. We have completed the implementation part.